Second talk of the session is about separation logic for concurrent randomized programs. The authors are Joe Tassarotti and Bob Harper, and Joe will give the talk. Take it away.
Thanks. So in this work, we want to reason about programs which combine concurrency and randomization. So first of all, why is that an interesting combination to consider? Well, the idea is that concurrent algorithms can often use randomization to decrease the need for synchronization and contention. And that's important because those are often source of bottlenecks and slowdowns in concurrent setting. So that's why it's interesting. Why is it difficult to handle this combination? Well, the problem is that when we introduce these two effects, there are now two sources of non-determinism. First of all, we have the random choices made by threads, which introduces a space of possible outcomes. And we want to reason about that non-determinism in a quantitative fashion. That is, we want to weight outcomes by the probability that they occur. The second source of non-determinism arises from the scheduler, which is going to determine the order that thread operations run in. And we want to reason about that in an adversarial fashion, in the sense that for any possible scheduler, we want to show that there are good properties of the algorithm. Okay, so to be a little bit more formal, the idea here is when we consider executing a current randomized program E from some starting state sigma under some scheduler phi, we're going to get some distribution of possible values. And as we change the scheduler, that will induce a different possible distribution. And we want to analyze these distributions in a way that will hold for any possible choice of scheduler. So to illustrate the principles here, I'm going to give an example of a concurrent randomized algorithm developed by Dice et al. That was published in SPA a few years ago. So the idea here is we have a concurrent counter that multiple threads should be able to increment and read from. Okay, so we're going to store the value of the counter in a reference cell. And reading from the counter is very simple. Just dereference and return the value. To do an increment, what a thread is going to do is it's first going to read the current value of the counter, store that in some variable k, and then it's going to generate a random Boolean, b, which will be true with probability 1 over k plus 1 and false otherwise. And if the Boolean is true, it's going to atomically add k plus 1 to the value in the counter. And otherwise, if the Boolean is false, it leaves the counter value unchanged. So obviously, when we read now, we're not going to get the exact number of increments. We're just going to get a probabilistic value. But the point here is that each call to increment in expectation, that is on average, is going to add 1 to the counter. So if we do n increments, the expected value of the counter will be n. Okay? So what we want to consider here is how do we formally prove that we have this property that the expected value will be n. Okay, so in our work, we present a program logic called Polaris, which is able to reason about this combination of concurrency and randomization. And we've proved the soundness of the logic and used it to verify two examples, the concurrent approximate counter and a concurrent skip list, all of the proofs being mechanized in Coq. And the key to our approach is that we build on sort of 3 lines of related work. The first is the probabilistic relational Hoare logic of Joe Barton and his collaborators, where they've identified the notion of coupling from probability theory as being key to doing probabilistic relational reasoning. Secondly, our separation logic Polaris is built as an extension to Iris, a state-of-the-art concurrency logic which has all the features we need to reason about fine-grained concurrent algorithms. And then finally, we use an idea from the denotational semantics community, what's called the monad of index valuations, which we're going to use to model these two effects of adversarial non-determinism and probabilistic choice. So let me sort of give a diagram that illustrates the approach we advocate in this work for reasoning about these algorithms. So we start with some concurrent randomized program, and then we're going to write a model or specification of that program's behavior in this monad of indexed valuations. And using Polaris, the separation logic, we're going to establish a correspondence between the behavior of the original algorithm and this model. And then we're going to use various calculational rules to derive quantitative properties like expected values and bounds on probabilities of events for this monadic model. And using the relationship between the model and the program established in the first step with the separation logic, we'll be able to translate back these quantitative properties into bounds on the behavior of the starting program. So I'm going to use this diagram to sort of outline the process, and I'll go through the steps throughout the rest of the talk. So first, let me just say some more about this monadic language we're going to use to write these models of these algorithms. So as I said, we're going to use this monad of index valuations, which was developed by Vrock and Winskell several years ago. And what they do is they first define a structure they call an indexed valuation, which you can think of as a probability distribution, which has some sort of auxiliary data for tracking how a probabilistic value was computed. And they show that this forms a monad with operations for probabilistic choice. And then they show that if you take non-empty sets of these index valuations, you get a monad that has both probabilistic choice, which we'll write as a plus with a circle subscripted by a probability p. And that means we're going to execute the left operand with probability p and the right operand with probability 1 minus p. And then there's also an operation for non-deterministic choice, which is just represented as the union of these two sets of outcomes. Okay, so let's see now how we will use this monad to write down the models of the concurrent algorithms we're interested in. In particular, I'll show the model for the approximate counter. So on the left, I have the concrete code for this algorithm that I showed earlier. And on the right, I have the monadic specification we want to consider. So first, we define a monadic function which simulates the process of performing an increment. So the first step is we need to simulate the process of reading from the counter, the current value in the counter, and binding that value to k. So when we read from the counter on the left, the value we're going to get is non-deterministic because other threads may be performing increments, so we don't know in advance what the value will be. So on the right, we simulate that by just non-deterministically returning some natural number value. Okay, and then we're going to generate a random Boolean on the left, and on the right, we simulate that in the monad by using this probabilistic choice operator, where we're going to use the probability 1 over k plus 1. All right, and then, rather than using explicit state to track the current value of the counter, we're going to model the effect of performing multiple increments with this functional representation of prox n below, which takes two arguments. The first is the number of increments to perform, and the second is the accumulated value stored in the counter. So if there are no more increments to perform, we just return it. And if otherwise, we first execute approximate increment and then recursively call it accumulating the value. OK, so now we have a way to model the algorithm in this sort of cleaner fashion. And now we want to discuss how we're going to analyze the quantitative properties of this model. So Vrock and Winskell just were mainly using this to give denotational semantics of languages with these features, but we needed to define some new notions. So in the paper, we describe how to define the expected value of a function on an index valuation. And it's very similar to the classical definition of an expected value of a random variable on some distribution in probability theory. Okay. And then since we're working with sets of index valuations, we lift this expected value operator to a set of index valuations. And then what we're going to get is a range of possible expected values. And what we're interested in is considering the minimal and maximal expected value you can obtain. And that's just defined as the infimum and supremum of applying the expected value to each index valuation in the set. And then since almost every notion in probability theory can be defined as an expected value, for example, probabilities can themselves be defined as the expected value of binary random variables, we're able to encode almost all the notions you'd want to consider in probability theory as appropriate expected values. So the nice thing about the definitions we have here is that there are sort of straightforward compositional rules for calculating the minimal and maximal expected values of suitably defined sets of index valuations. So I'm going to show some of those rules here. If we want to compute the minimal expected value of a probabilistic choice, well, that's just the weighted sum of the minimal expected values of the operands. The minimal expected value of a non-deterministic choice is the minimal expected values of the two operands. if the computation always just returns some constant value, then the expected value is going to be the function f applied to that value. And then the expected value operator is a linear operator in the sense that if the function we're computing the expected value of involves multiplication and addition of constants, we can pull out that multiplication and addition. So these are sort of familiar if you're used to considering classical expected value operator, and those properties are preserved when we move to the minimal and maximal setting. And the rules for maximal are the duals. So let's now apply these rules to calculate the expected value of the model of the approximate counter. So what we're going to show is that the current value in the counter is L, and we do n more increments, then the expected value is going to be n plus L. So the main step is to just show that each time we do approximate increment, it's going to add 1. And just by unfolding the definition and applying the rewrite rules I showed previously, we compute that indeed it is 1. All right, so we've got our monadic model. We've got a way to calculate expected properties of that. And now we just need to link that back to the program we started with, for which we're going to use Polaris, the separation logic. So as I said, the separation logic itself is going to draw on concepts from the probabilistic relational Hoare logic of Jill Bart and his collaborators. And in that work, they started with Nick Benton's relational Hoare logic, in which instead of considering Hoare triples about a single program E, we're going to now consider Hoare quadruples, which relate to two programs E1 and E2. And instead of pre and post conditions, these P and Q are now pre and post relations. So what probabilistic relational Hoare logic adds to Benton's relational Hoare logic is a new rule for when both E1 and E2 make a probabilistic transition. And what they say there is that one has to exhibit what's known as a probabilistic coupling between the two distributions of possible transitions. So I won't give the definition of coupling. Justin Su's dissertation explains very cleanly this idea. The reason I won't give the details is because we're going to have to change the notion when we now move to our setting. So in particular, we need to modify these concepts in two ways when we consider the concurrency. So as I said, our work is an extension also of IRIS, a concurrent separation logic. And so what we're going to need to do is, rather than relating two concrete programs E1 and E2, we want to relate a single program E to this monadic specification script I. And we also need to not work with couplings, which are from classical probability theory. We need some generalization to consider the fact that we're working with index valuations and sets of index valuations. So to deal with the first issue, we're going to use what's become sort of a standard trick in concurrent separation logic world, which is rather than considering Hoare quadruples, we're going to represent the monadic model that we want to relate to our program as an assertion in the logic. Because it's a kind of specification of the program's behavior, that's a very natural consideration. So we're going to add a new assertion to IRIS, which we write prob of script I, where this is the monadic computation we want to consider. And then rather than proving Hoare quadruples, we're just going to prove Hoare triples, where the precondition will contain this assertion for the model we're trying to relate to E. All right? And then, as I say, instead of using couplings, we define in the paper a notion of non-deterministic coupling. So when one of these couplings exists, we have this judgment of this form, where on the left we have a single index valuation I, and then a set of index valuation script I, and then there's an annotation R, which is a relation on the return values of I and script I, which you can think of as a kind of post relation. And what we're going to see is that this judgment has the structure almost of a mini Hoare logic itself, which we're going to embed in the larger program logic. So I'm just going to show some of the rules we use to derive the existence of these couplings. So if we're trying to consider a program which always just returns a constant value A, and we want to relate that to the singleton set, which also always just returns a constant b, and we know that the relation R holds for A and B, we can derive the existence of a coupling. Right? Then if we're considering computations which are both making probabilistic choices with some common probability p, it suffices to exhibit a coupling between both the left operands and the right operands, respectively. So this rule, there's a very analogous form in the probabilistic relational Hoare logic. Okay? So we recreate that same sort of reasoning. But then in addition, now we also need to consider reasoning about non-deterministic choices. So we have a rule that says, well, if we want to relate a single I to a non-deterministic choice between script I and script I prime, it suffices to just show that I is related to either of the operands on the right, and there's obviously a symmetric rule for when we want to relate to the right operand. So using these rules, we can show the existence of these non-deterministic couplings. And then we extend Iris with just one new rule, which involves these couplings when we're reasoning about probabilistic commands. So in particular, if we want to reason about a command that's going to generate a binary choice with probability p, and our monadic model is going to execute script I and then continue as f, then above the line we have to exhibit a coupling between a probabilistic choice of true and false with probability p and the monadic model script I. And we get to pick the post relation R. And then below the line, in the post condition of our Hoare triple, we'll get that the return value of flip p, which will be bound to b, and the return value of the monadic model, which will be bound to x, will be related by that same relation R. And in particular, the monadic model will now be updated to f of x. Okay? So we just add this one rule, and all of the other Iris rules and features are the same in our extension, which means we can reuse Iris proofs and techniques for reasoning about non-probabilistic components of our algorithm, like locks and stacks and so on. Okay, and then the soundness theorem for the logic says that if we prove a triple about a program E, where in the precondition we have some script I, and in the postcondition, the return value of the program E is equal to the return value of the monadic model after applying functions f and g, then the expected value of f applied to the execution of E will be bounded by the extremal expected values of script I applied to with g. So in other words, we now have a way to bound the expected values of our concrete code just by considering the expected values of the model, which is what we were after. Okay, so just to wrap up, again, we've developed a separation logic for reasoning about these combination of features. We've verified two examples, the counter and a concurrent skip list. And we've drawn on these 3 lines of related work to be able to do so. Thanks.
Thanks, Joe. Okay, so if you want to ask a question, please come to the front, and I'll give you that microphone. So we can start with a question from Slido. So the question is, so why is there a difference between non-deterministic choice and probabilistic choice with probability 1/2? Isn't that the same thing?
No, because we want to consider a scheduler which could say always just consider one choice. If you baked in 1/2, you would get a particular expected value, but the scheduler could be far more malicious and consider extremes that skew the probability.
To what extent can your framework work with programs that not almost surely terminate? So they have, let's say, a positive probability of divergence.
Yeah, so in our soundness theorem, I didn't say it out loud, but it's below, we assume that there's some upper bound across all executions.
So here's another question from Slido. So what if determinacy of a loaded value depends on the precondition? Could you model that?
Say one more time?
The determinacy of a loaded value from a shared.
Yes, we can reason about that. Yeah.
Okay, so yeah.
So if I understand well, your logic works for discrete distribution.
Yes.
Do you have an idea on how to extend it to continuous one?
So part of the problem there is that we then need a monadic representation for non-deterministic and probabilistic choice with both. The index valuations don't handle that, but there are alternatives that do. So maybe if we use that instead, we'd be able to handle both.
Okay, so let's thank Joe again.